Excellent. You guys, let's get flying. So before I get going, I'm going to show you guys this video real quick. I just made a video for you guys. It's going to go on and on. So this is a GIF I made for explaining how absorption and emission spectra work. Why is there an emission spectra? Why is an absorption spectra? Can I get rid of this? How do I get rid of this thing here? Okay. So what's going on here is, let's say we have a sun here, and here's a cloud of gas. So the cloud of gas is here, and the light of the sun is going through that cloud of gas. That light is heating up this cloud of gas too. So this cloud of gas is getting hot. What does that mean? What does temperature mean? It means that the atoms are moving fast, right? So if you have temperature, that means you're moving around. It's the measure of temperature, right? It's a measure of how fast the atoms are moving. So if atoms are moving pretty fast, there could be collisions. If there are collisions, then the electrons don't have to sit in the ground state. They could be excited. So if the atoms are excited, that means the electrons will be in the second or third, all right? So what we have here is, in one case, we have the electron in the second. In this case, we have the electron in the third level of the hydrogen atom, all right? Let's take a look again. This one is in the second level. This one's in the third level. Maybe there was a collision or something, right? So as the photon is coming from the sun here, you see the photon is coming in like this. As it comes in, he sees an electron in the second level of the hydrogen atom. The electron absorbs it, goes to the third level. Let's watch it again. The electron gets excited, goes to the third level. It doesn't let the photon get through. So in this case, we have an absorption. Photon is gone. No more photon. So in its place, we get this dark line, all right? So this dark line is telling us the absence of a photon. It's telling us that there were a lot of electrons, and these electrons were exactly in the right place, in the second orbit of the hydrogen atom. When that red light came in, the red light was absorbed in this case. So the red light never even got through. It was absorbed. So when we get the spectra, when we put a prism in front of the light, what we see is an absence of that very specific photon. This photon is very specific. It happens when an electron is coming down from the third to the second level. So now let's watch this emission now. This one here is already in the third level, and it comes down to the second level. Look at it, it's coming down. As it comes down, it gives us a photon. One more time. This one here comes down from the third to the second. It gives us exactly the photon that was, absorbed here. So in one case, we have the absorption of that photon, that beautiful red photon here. In one case, we have an emission of that red photon. Now I'm waiting for questions so we can get this out of the way. So emission is when the electron is going down. Absorption is when the electron goes up.
Okay, so I can ask a question.
Of course.
Once the electron has absorbed the photon, why then is it coming down in orbit?
It's not coming down. It absorbs it and goes up. Look,
right.
It goes up.
But then you say it comes down and it.
Oh, this is another atom altogether. What happens here?
It didn't absorb it. Is that what you're saying?
No, in this case, it absorbed it. It's gone.
Yeah. In the bottom one.
It's the end of the story here. This is another case. This is another atom. This is two atoms here. One atom is doing the emission, is emitting light. One atom is absorbing the light. This one has just absorbed that photon. The photon was coming in. It never got through. It hit the electron.
Yes.
And absorbed it. So that one is gone.
Okay.
This one here is another atom. This one here is sitting in the third level. And now it comes down to the second, and it gives us this beautiful photon. So in one case, the electron is coming down in orbit. In one case, the electron is going up in orbit. When you're going up, you're absorbing. When you're coming down, you're emitting.
Okay, thank you.
More importantly, though, one of them is going from the second to the third, that one. And the other one is coming down from the third to the second. So the light that we see is the difference between the energy of the second and the third level of the hydrogen atom. the difference in the energy is this beautiful red light here. So in one case, it absorbs that photon. In one case, it emits that photon. In one case, it comes down from the third to the second here. In one case, it goes up from the second to third.
Professor, I have a question.
Yes, please.
So an atom will only emit light when it's in emission, right? Where it's when it's going down a level and emitting a photon.
Correct.
Not when it's absorbing.
Correct. Now, what happens after it absorbs it, I have no idea. It could go up to the third. It could come down to the first. It gives us, ultraviolet, or some other photon can come and hit it and knock it out altogether. So we don't know. We just know that that photon is gone. So that photon is gone. That very specific photon is gone. It's been absorbed. So in its place, we're getting a dark line here.
I have a question.
Yes, please.
Do the lines on the bright line spectrum, are those the same as the dark lines on the continuous?
Very good.
Dark line
Exactly
spectrum?
right. Yes. I have forgotten to give you guys some points. I should give you guys more points. So who just asked that last question?
Trevor.
Trevor, what's your last name?
Shaw. S-H-A-W.
A-W. Thank you very much. That was a great question. That's right. Yeah, if you compare, these are exactly the same lines here. Each one of these lines represents the difference between one level in the hydrogen atom to another level, right? So, like this one is coming from the fifth to the second. This one is from the sixth to the second, like that. This one is an electron going from the second to the fifth, like that. All right? Okay, so let's keep going here. So today we're going to be talking about isotopes, nuclear bombs, hydrogen bombs. And is there a reason I'm talking about hydrogen bombs and nuclear bombs? Yes, there is definitely a reason for it. Because that's what the energy of the universe is. Energy of the universe is inside of the atoms. All the atoms that you see here in the periodic table of the elements, they have hidden energy. All of them have hidden energy. Lots and lots of incredible amounts of energy hidden. So when we look at these atoms, number one, we're looking at hydrogen. And hydrogen says 1 on top, right? So if you look at it on top, it says 1. It's telling us how many protons hydrogen has. So if you have 1 proton, you're called hydrogen. If you have 2 protons, you are called helium. So this is called helium, this is called hydrogen, because of the number of protons. So if you look at carbon, 6 protons. If you look at oxygen, 8 protons. So the number of protons determines the element. I know that's going to be one of the questions on the next exam, so please make some kind of a note. The number of protons determines the element. It doesn't matter how many neutrons you have. It doesn't matter how many electrons you have. That doesn't change the element. Only the number of protons. So silicon, glass, silicon, 14. So if you got 14 protons, you call it silicon. Now, there's something else though. There's another number here. If you look on top, 5, 6, 7. If you look at the bottom here, it says 10.81, right? 10.81, that's some kind of error there, I think. 12.001, 14 point whatever, right? So what's that all about, right? There's another number. This is called atomic weight. So I'll tell you the definition of atomic weight, then I'm going to show you slides to explain what this atomic weight exactly is. By definition, the atomic weight is the average number of protons and neutrons as seen in nature on Earth. In other words, when we go check out atoms on Earth, we average to see how many neutrons they have as well as protons. So helium has 2 protons. Its atomic weight says 4.0026. This is an average. What the heck kind of an average is it? That's what I'm going to explain now. What does this mean? So number of neutrons gives you what is called an isotope of an element. So isotope of an element is the same number of protons, different number of neutrons. As an example, here's hydrogen. You got one proton, you're hydrogen. That's it. Done. Hydrogen. So this hydrogen doesn't have any neutrons. In fact, it doesn't even need any neutrons. Why do atoms need neutrons anyways? Well, it turns out the number of neutrons has to do with the stability of the atoms. Well, what does that mean, stability? Well, all atoms are decaying. All atoms in nature are decaying. In time, there'll be no atoms left in nature. Nothing. Like in 500 billion years, there may be no atoms left in the universe. You come back to the universe in 2 trillion years, you might not see anything. Not a single matter in the universe. Only light and space, probably, right? So what's the deal? Let's take a look. This is called an isotope of hydrogen because it has, no neutrons. It's just one proton. This is hydrogen, but it's got one neutron. So this is an isotope of hydrogen. This is another isotope of hydrogen. So the number of neutrons gives us different isotopes. Now, does hydrogen need a neutron? No, hydrogen doesn't need a neutron to stabilize it. On the other hand, this element here does need neutron to stabilize it. It's got 2 protons, so this is called helium. Helium in nature is most stable when it has 2 neutrons. So you got 2 neutrons, 2 protons, very stable. Well, what if you are, helium, but look this, no neutrons, not very stable. How about if you have 3 neutrons, not stable. This, by the way, is called helium-5. Because it's got 1, 2, 3, 4, 5. This one here is called helium-2. This one here is called helium-4. So they add the number of protons to neutrons, and they say this isotope is helium-4, helium-2, helium-5, like that. Now we average it. So 5 plus 2 plus 4 plus 3 plus 6, It turns out that in nature, when we look at helium, on average, helium has 4.0026. That means if you have 2 protons and 2 neutrons, you're the most stable. If 3 neutrons stabilized you really good, then this will be 5, not 4. If 4 neutrons stabilized helium, this would be helium-6. You have 4 neutrons and 2 protons, like that. So that's why there's this fraction here, 4.0026. That means almost all helium atoms have 2 neutrons. If you have more than 2, if you have less than 2. When we average them all out, it appears that more helium atoms have 3 than 1. But most all of them have 2. So when you average them out, you get 4.0026, like that. So that's what that number represents, all right? So why did I talk about isotopes? Because we want to talk about this guy here, right? Uranium. Let me see if I can bring uranium to the center. This is called uranium. Uranium has 92 protons. That's a lot of protons. Now, here it says 238. That's an isotope of uranium, 238. So how many neutrons does uranium-238 isotope have? Well, you subtract it. You go 238 minus 92. That gives you 146 neutrons. So uranium atom gets very stable. It's the most stable of all the uranium atoms when you have 146 neutrons. Well, what if you have 147? Well, you're good, but you're not as stable as 146. What if you had 150? You're not as stable again. as if you had 146. So 238, it turns out that after billions and billions of years on Earth, which is like a laboratory, right? We find ourselves on Earth after billions and billions of years. So this tells us a lot. What we find tells us how things disintegrate on Earth, right? And so we find that uranium-238 is what we find in the mine. That's the most stable form of uranium. It's 146. Now, what if you had uranium-237, uranium-236, uranium-235? Not stable. They're not as stable. In fact, they're used in bombs. Uranium-235, uranium-236 is what you use in bombs, right? So how does that work? Well, if you have uranium-236, which has 2 less neutrons than uranium-238, then this is what you look like. You have a nucleus full of neutrons and protons, and you have lots and lots of electrons and such. So that's what we find. This is called yellow cake. You find yellow cake in a uranium mine. Over time, this uranium-238, it disintegrates. It becomes uranium-237, uranium-236, uranium-235. It loses neutrons, right? It decays, basically. That's what it's called, decaying. So if you find yellow cake in a mine, there is uranium-238, most of it. Some of it, very few, are uranium-235. A few are uranium-236. They used to be 238 maybe, and now they're 235, 236, something like that. We use that because it's so unstable. We use it and we shoot neutrons at it. You shoot a neutron at the uranium-235 or 236, look what happens. It splits up like that. That's the basis of atomic bomb. So where's all of the energy come from? Well, that's the key thing. The key thing is this. When we look at this uranium atom, let me go back here. This nucleus is held together. Why is this uranium together? You have all of these protons, and all these protons have positive charge. They should repel each other. Not 2 of these protons should be stuck together. And yet, we have 92 protons stuck together because protons are stuck together with a force that is stronger than the repulsion force. The repulsion force is the electric force, right? Remember, protons have a positive charge, so they repel each other. Well, there is a stronger force than that, the strong nuclear force. And that strong nuclear force, which is carried by a particle called gluon, gets exchanged between protons. So if the protons can be close enough together, like in the nucleus of the atom here, this fantastic force takes over, called a strong nuclear force, and it binds them together. It glues them together. So this entire nucleus is glued together with something called gluon, which is the strong nuclear force. It's carrying the strong nuclear force. When we split it, that strong nuclear force comes out. It's inside the nucleus of the atoms. It's hidden, and it comes out. Like if I had the energy extracted from something very simple, like a pin, I could destroy California. That's how much energy is hidden inside of a pin. Of course, if you really want to, get all the energy out of a pin, what you need is something even bigger than a nuclear bomb or hydrogen bomb. We'll talk about that later. That's another kind of bomb. Okay, so, all right. So then this is called fission. There's something else called fusion. That's the hydrogen bomb. And that's what works inside of the sun and the stars. This one here, fission, this works in the atomic bomb. Fusion works in the hydrogen bomb. So we'll talk about fission today. If I have time, we'll talk about a hydrogen bomb as well. So let me see if I can show you guys a movie first. It's just a few minutes of what this nuclear bomb is all about. Let me tell you something. When the US dropped a bomb on Hiroshima, it was 1945, I think. we killed 100,000 people. And it only took 1.5 grams. 1.5 grams, I tell you. That's all it took. So the energy that was hidden in 1.5 grams of uranium destroyed a city. It's incredible, right? Okay, so this is the very first nuclear bomb that was detonated.
At 5:30 a.m., dawn on July 16, 1945, near a small town called Alamogordo, New Mexico, the course of human history was changed. The first atomic bomb was detonated that day and sealed the fate of humanity. It took the work of many people to accomplish this engineering feat, but the principal leader of that Manhattan Project, and the man considered the father of the atomic bomb, was Robert Oppenheimer. After witnessing its awesome power on that fateful day, Oppenheimer was so taken aback, he quoted a verse from the sacred Hindu text, the Bhagavad Gita. Now I am become death, the destroyer of worlds. We know its awesome power, but how exactly does an atom bomb work? An atom bomb works on the principle that when you break up a nucleus of an atom, a large amount of energy is released. Why? Because it takes a large amount of energy to keep the nucleus bound together. When you split it apart, the energy is released. The analogy is like a stack of bowling pins. When you hit it with a bowling ball, all the energy that you used in stacking it is released. You can think of the nucleus of an atom being similarly stacked together. Physics purists may ding me for this analogy, but for the purposes of simplification, this is a good way to think of it.
I don't think so. That's a very bad way to think about it. So please don't think about it that way.
Scientists chose the biggest, heaviest nucleus that is found in nature to be the best candidate for splitting, uranium. Uranium is unique in that one of its isotopes is the only naturally occurring element on Earth that is capable of sustaining a nuclear fission reaction. A uranium atom has 92 protons and 146 neutrons. Together, they give it an atomic mass of 238, the U-238. A very small portion of uranium, when it is mined, is in the form of an isotope, U-235. This isotope has the same 92 protons, but only 142 neutrons, or 3 fewer than U-238. U-235 is highly unstable, which makes it highly fissionable or splittable. When uranium U-235 is slammed by a neutron, it becomes uranium-236. U-236 is so unstable that it almost immediately splits into 2 more stable atoms, krypton and barium. In the process of splitting and creating 2 more stable atoms, a whole bunch of energy is released, along with 3 more neutrons. These 3 neutrons fly out and slam more U-235 atoms, and thus a chain reaction occurs, causing more and more U-235 to be split, and ultimately causes a huge explosion. So what's the big deal? Why don't more countries have the bomb? Well, the problem is that natural uranium contains only 0.7% of this U-235 isotope, and a whole bunch of it is needed to make even one atomic bomb. So mined natural uranium has to be enriched to get U-235. Sometimes this enrichment is done by turning it into a gas and letting the lighter gas flow through a one-way barrier so that it rises to the top. Because U-235, as you might guess, is lighter than U-238. Another engineering challenge is to create a vessel with the correct shape and material to contain the neutrons after fissioning so that they do not escape, but rather cause more atoms to fission. And it is lined with a special mirror so as to force neutrons back into the fissionable material rather than escape the vessel. Then the correct amount of fissionable material has to be placed inside this vessel. This is called supercritical mass. There has to be enough mass to sustain an uncontrollable chain reaction, resulting in an explosion. And finally, the supercritical mass has to be kept apart until you're ready for an explosion. Otherwise, an explosion can occur when you don't want it. The reason is because these isotopes are unstable and are throwing off neutrons randomly. So the mass has to be kept apart so that it is subcritical until ready to be exploded. In an atom bomb, 2 subcritical masses are slammed together, usually with a conventional bomb contained inside the outer bomb. This conventional explosive charge inside the container initiates the chain reaction to produce your typical mushroom cloud. And where exactly does all that energy come from? It comes from Einstein's famous equation, E equals mc squared. The mass of the material left over from the nuclear bomb is slightly less than before the explosion, only about 0.1% less. And that 0.1% is what causes that huge explosion. Imagine how big that explosion would be if all the mass, 100%, was converted to energy. We need to thank our lucky stars that although the concept of an atom bomb is simple, the process of actually creating a bomb is not so simple.
All right. Any question, you guys? If there are no questions, I am going to give you guys.
I have just a clarification. So fission is when a neutron is pushed into,
Go ahead.
for example, a uranium atom.
Correct. Well, it hits at a very high speed. In fact, I am going to give you a little more description about how to make a bomb. Not that you guys are going to be able to make a bomb unless you have the material and all that, but if you did, you're not going to need my help. But yeah, let me just show you how this is done. It's not that difficult. So you get yourself a little container you want to put all your bomb in, right? So you get something like this, like a little football. Remember, inside is like mirrors. It's a special mirror so that when you have all these stuff coming out, all these neutrons coming out, trying to break apart the other atoms, you know, they don't escape. So they're going to be inside here. So you put some of this material here. So uranium-235. Uranium-235. You put some of that stuff here. All right, now, you got to get this thing going, right? You got to start it up, right? So how do you start it up? Well, you start it up with a dynamite. So this is a detonator. So you got to stick a dynamite here. And you light it up. You light up the fuse, and when the dynamite goes off, then fission begins. So fission, right? Fission means that neutrons are going to fly off and break apart atoms here. When they break apart, then more neutrons are released. And these neutrons come and hit these guys here. And these guys in turn go like that. So this, in just a fraction of a second, this is unstoppable. Back and forth they go, and bang, 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 the whole thing goes up. So this is called the atomic bomb. Atomic bomb. That's all it is. Now, this atomic bomb, you're going to laugh at this. This atomic bomb, the whole bomb, the atomic bomb, is the detonator for a hydrogen bomb. So, which means this. You see this dynamite here? The dynamite to the atomic bomb is the same as the atomic bomb to a hydrogen bomb. So we start the atomic bomb with this dynamite. We start a hydrogen bomb with the atomic bomb. Atomic bomb is a detonator. It just starts it up. So you can imagine, like, it's 1,000 times more powerful than a nuclear bomb. So this hydrogen bomb must be fantastic, right? It is fantastic. But that's something else we call fusion. So the act of fusion, what we call a hydrogen bomb is actually putting hydrogen atoms together. Instead of taking the atoms apart, we're going to put them together. Who does that? The entire universe does that. Is there anybody in the solar system that is doing it? Yeah, the sun. That's how the sun makes all of its energy. It's like not billions, probably millions of hydrogen bombs going off simultaneously every second. Billion hydrogen bombs just went up. Another billion hydrogen bombs just went up inside the sun. It's continuously doing that. All right, so in this case here, we said 0.1% of the mass turns into energy, right? just a tiny fraction of it turns to actual pure energy. So what does that mean? Let's take a look. We said E is equal to mc squared, right? So E is equal to mc squared. E is equal to mc squared. Famous Einstein's equation. Except Einstein never wrote it this way. What Einstein wrote was m mass is equal to E divided by c squared. This is the original formula. So what does it all mean? It means this. So what it's saying is energy, E is energy, energy is equal to mass times, you have to multiply this, times the speed of light to the power of 2. Speed of light to the power of 2. That's a huge number, to the power of 2. So it's the same thing that fusion does. Fusion is the act of putting stuff together, like hydrogen atoms put together. You get a lot of energy as well. How that happens is what we're going to do next week. All next week, we're going to do energy production in the sun. We're going to be talking about the sun itself. So let's take a look. How much energy can I get from 1 gram? 1 gram, you know, that's about the size of a sugar cube, like a little tiny sugar cube. How much energy can I get out of a sugar cube? Let's take a look. So we say the energy is equal to 1 gram. Let's just make it very simple because the number is 1. So we multiply 1 times the speed of light to the power of 2. What is the speed of light? Well, the speed of light is 300,000 kilometers per second. I'm using grams. So because we're using grams, let's use centimeters per second, not kilometers per second. So this would be 3. Okay, that's the speed of light to the power of 2. This is centimeters per second. That's the speed of light. All right, well, let's do it. Let's see how much energy I can get from it. Okay, so we say energy is equal to, well, 1 is 1, so I don't have to worry about 1. I'll just get this number to the power of 2. So I get 9. All right, so what is this number? I think it's 900 quadrillion, right? 900 quadrillion. Million, billion, trillion, quadrillion. 900 quadrillion ergs. That's the unit of energy here. Now, erg is not a very big unit. You know, it's not a lot of energy. 1 erg is as much energy as it takes little fly or a little mosquito to fly. How much energy does it take for a mosquito to fly? But you have a feeling how much energy that is, right? Well, that's just how many mosquitoes are going to be taking flight. 900 quadrillion mosquitoes. Pretty much they can take San Diego and make it fly. That's how much energy. So just a little bit, right, of mass that turns into energy. It gives us out fantastic amounts of energy. Now, the sun is very massive. Very, very, very massive, right? How massive is it? Let's see how massive the sun is. Sun is 333,000 times the mass of the Earth. Volume of the sun is about 1,000,000 times the volume of the Earth. That means you can put 1,000,000 Earths in the sun to fill it up. 1,000,000 times the volume of the Earth. So if you have this much mass and this gas, it's just a big ball of gas, hydrogen gas. That means hydrogen, right? And this hydrogen is very simple. 1 proton. Electrons are not playing with the protons in the sun. In the sun, we have ions. Let's see if you guys remember ions. Ion means charged atom. 1 proton has got a positive charge. If it has an electron, it's neutral hydrogen atom. But one proton itself is a positive hydrogen ion. That's what the sun is made of. Very simple. Protons, just protons. That's it. Whole bunch of protons. That's what the sun is. So this whole bunch of protons in the form of a gas, you put it together, it's 1,000,000 times the size of the Earth. It's like 333,000 times the mass of the Earth. Well, how much gravity does this thing have? Incredible amounts of gravity, right? All this gravity wants to shrink this gas and make it into a black hole, basically, right? But it can't. Why can't it? Because the sun, in its core, makes so much energy that it sustains its own mass. It doesn't shrink, it doesn't expand, it stays the same size for billions of years. Very stable, the sun is. All it is, it makes energy from putting stuff together, putting these hydrogen atoms together. Now, I started putting something together for you, but I'm not totally done yet. Let's see. So here's the simple way of doing this. Two protons coming together. One of them turns into a neutron. One of them stays a proton. So let me do it one more time. Two protons hitting each other, and then a positron is ejected. Positron is antimatter to an electron. So an electron with a negative charge, we have electron with a positive charge. It's called a positron. A positron comes out when you have two protons hit each other head on at a very high speed. So why do we need all this high speed? Well, you need high speed because of this. One more time. Because when two protons get very close to each other, they will repel each other. The two protons need to get very, very, very close to each other so that that super duper strong nuclear force reaches out and glues the two together. Unless they're very, very close together, they wouldn't be stuck together. They just repel each other. But when they get moving at close to, speed of light or 10% of the speed of light, like this, bang, they stick together. When they stick together, one of them becomes a neutron, one of them stays a proton, an electron with a positive charge comes out, and that's called a positron. And then this thing comes out. This thing is called a ghost particle. Why is it called a ghost particle? Because it goes right through the Earth. It goes right through everything. It goes right through the sun. Nothing can stop this ghost particle, right? It's called a neutrino. A neutrino goes through the Earth. It goes through everything. So this neutrino is called a ghost particle, and a ghost particle comes out. This is just one of the first steps that we're going to be discussing next week. This is the very first step. Two protons come together. They stick together. One of them becomes a neutron, and then when it becomes a neutron, the charge of the proton is shot out in the form of a positive electron called a positron, antimatter to an electron. Now, this antimatter stuff is incredible. If you have antimatter bomb, that means like regular matter and antimatter. Antimatter is like a proton with a negative charge, electron with a positive charge. So all of this is antimatter. Antimatter hits matter, then you get 100% energy production. That's the best bomb you could possibly make. If you had, let's say, a car made of antimatter, and you dropped it on the Earth, the entire Earth will be pieces. It'll destroy the Earth. That's what happens to the Earth. That's all you need is antimatter bomb. Now, when we see each other next week, we're going to finish this cycle. So we have two protons coming together. Here we have a positron come out and a neutrino. And so what we get here, what we just showed you, is a neutron and a proton. And that has a name. It's called deuteron or deuterium, which is a hydrogen isotope, a hydrogen proton with one neutron. And so when that happens and it hits another proton, then it becomes a helium. So you're making helium. And when two helium atoms hit each other, then you make helium-4. All of this seems very simple. Two protons hit each other, they become heavy hydrogen, one proton with one neutron. They hit another proton, they turn into helium, two protons, one neutron. Then these two, one of these, and one of these, a neutron with just, a helium atom with just one neutron. They collide at high speed, and then they make helium-4, two protons and two neutrons. Very, very simple. That's how the sun makes its energy. This is also how you make a hydrogen bomb. You need to go at very, very high speeds, incredibly high speeds, because if you don't, the protons don't get close enough together for that gluon to reach out and grab the protons and stick them together. Otherwise, they'll just repel each other if they go at a slow speed. So you need a nuclear bomb and a canister of hydrogen. When you got that, you got yourself a hydrogen bomb. So we're going to start with a hydrogen bomb next week. Next time I'll see you, we're going to make a hydrogen bomb. And we're going to show you how, when you start with hydrogen, you make Mina, you make Kelsey, you make Alondra, everything that you know, everything you've ever seen, everything that is in existence came from this process. You start with hydrogen, you go all the way to the end of the table, you make uranium from the same exact process. Who does this? The stars. Only inside of the stars. And you have to have very massive stars. Only inside of a very, very massive stars, you make all the elements on the periodic table. So that's where we come from. Like Linda and Marcus and Mina, you're all together. Every one of you, we're together. We're all what you call Stardust brothers and sisters. All right, so all the Stardust brothers and sisters, all of us were at one time inside of a very massive star, humongous star. We're moving around. What are the possibility of Linda's atom meeting Kelsey's atoms? What's the possibility? 100%. What's the possibility of Sina's atoms hitting Hitler's atoms? 100%. My atoms and Hitler's atoms pass by each other. Yeah, we're all together. So we're all Stardust brothers and sisters. All right. So thank you so much, Stardust brothers and sisters, for coming to class today.